Okay, welcome everyone. My name is Hugh Price. I'm the academic director of CSER. This event marks 1 year that we've now been running monthly lectures. And of course, this is our first in our new home here in the David Attenborough building, and we're delighted and very grateful to the Cambridge Conservation Initiative for hosting us here. I hope that some of you here are from the CCI. And that you'll enjoy this talk and treat it as an excellent example of the kind of thing that CSER is involved in. I think we've got a really fascinating talk this afternoon with two speakers who are 2 out of 3 members of a collaboration. I'm going to introduce them very briefly indeed, because of course you're here to hear from them and not from me. The first main speaker is going to be Professor Stephen Briggs. Professor Briggs trained as an astrophysicist, but is currently senior advisor to the European Space Agency and chair of the UN Global Climate Observing System. And previously he headed the Department of Earth Observation, Science, Applications and Future Technologies of the European Space Agency in Frascati, Italy. Our second speaker, Professor Charles Kennel, is Director Emeritus, Vice Chancellor and Distinguished Professor Emeritus at the Scripps Institution of Oceanography at the University of California, San Diego. And here in Cambridge, he's a Distinguished Visiting Scholar at Christ College and a Visiting Research Fellow at the Center for Science and Policy. Now, he's had a very long and distinguished career. I'm just going to give you, as appropriate to the topic of today's talk, a kind of satellite snapshot of just one tiny part of it. This is from the CSAP website, which says from 1994 to 1996, Professor Kennel was Associate Administrator at NASA and Director of Mission to Planet Earth, a global Earth science satellite program. Kennel's experience at NASA influenced him to go into Earth and climate science, and he became the 9th Director and Dean of the Scripps Institution of Oceanography and Vice Chancellor of Marine Sciences at UCSD, where he was founding director of the UCSD Environment and Sustainability Initiative. That's something like a 2-year snapshot of Charlie's remarkable career. The third member of the team, unfortunately not with us today, is Professor David Victor, a professor at the Graduate School of Global Policy and Strategy at UCSD, and director of their new laboratory on international law and regulation. He's a political scientist qualified at MIT and Harvard, and his research focuses on how design of regulatory law affects issues such as environmental pollution and the operation of major energy markets. And he's the author of the book Global Warming Gridlock. Okay, so that's our speakers, our 2 speakers and their collaborator. Now, I understand that, Charlie, you're going to provide a very brief introduction. And then we're going to hear from Stephen. So welcome to both.
Fortunately, you said most everything that I wanted to say. The introduction was a bit fulsome, but that's all right. This is a collaboration, and you're going to get 2 speeches, one from me and one from Stephen, and it splits up nicely because Stephen is going to... I should say that our collaboration self-assembled from different starting points. And David and I in one starting point, and Stephen from another, and we came together. And so each of us is going to explain how we got into this topic. And Stephen will do so first by telling us a bit about the planetary vital signs and what they are and what they could be if we can generate them, and will. And I will move on to planetary decisions, how we make decisions about the impacts of climate change, and then some highly speculative remarks about planetary intelligence, for which I hope I can be forgiven, but part of the blame falls on you, who encouraged me to go the visionary route. So I'm going to, and you needn't trust everything you hear at the end of this talk. So with that, Stephen is going to start, and then when we've figured out a neat little transition, and then I will get up and do sections 2 and 3.
Thanks very much. I'll stand over here because this is where the recording microphone is, so I won't wander around. So I'll talk for about 10 or 15 minutes about observations And observations are measurements of the world as it has been in the past and up until the current date. Obviously, we don't have observations yet of the future, and so the understanding of where we go in the future will come in the second part of the talk. So one observation you will all have heard about is surface temperature. The famous temperature, the famous hiatus, the argument point that's taken place for the last 10 or 15 years. And you see the sort of simple representation of it here, where there was this debate about whether the hiatus is real. Is this area really flat? Did global warming stop? And is climate change just something which scientists have invented in order to gain funding? Well, the first thing I'll say is that this is probably the worst possible parameter you could take in order to understand whether the world is changing. And I'll show you why in a moment. So you can see there's a general increase there, but you can see it's also affected very strongly by, well, there's random variation as you'd expect, but it's also very much affected by El Nino and La Nina events, major events in the oceans. And perhaps the best way of describing why this is such a bad indicator is to give you a much better one. And this is what's called ocean heat content, or in fact, to be precise, it's actually the total energy Earth system heat content. And it shows the way that the energy of the Earth system has increased over the last 50 years or so, as a result of the greater efficiency of the Earth system in capturing energy from the sun. So there's a number of things we should note about this. Firstly, it's pretty well monotonically increasing. You have little blips in 1983 and 1998 when there were very strong El Nino events, but more or less the energy of the whole Earth system is increasing pretty well steadily and without any hiatus. Secondly, the error bars are pretty small. So you have an error, but it's plus or minus 10% or something. So there's not really much argument about whether this increase is real or not. The third thing you should note is how it's distributed amongst the different components in the Earth system. So the light blue you see at the top is the energy which has gone into the top 700 meters of the ocean. The dark blue is the energy between 700 meters and about 2,000 meters in the ocean. Below 2,000 meters, we don't really know what's going on there, but probably not much. In white is the energy that's been absorbed in warming the ice and increasing the ice sheet loss. In yellow, orange is the energy that's gone into the land surface. And the little bit of red at the bottom is what's gone into measuring the temperature of the atmosphere, increasing the temperature of the atmosphere, which, if you remember, is the indicator that we've all been looking at ever up until now. In other words, we're looking at about 2% of the total energy in the system and having a debate about what's happening to that whilst ignoring the other 98%. The analogy I sometimes use, it's like seeing the last 2 inches of a dog's tail going past a window, then having an argument about what sort of dog it was, when actually if you just open the window you can see the whole dog. So this tells us that perhaps temperature is not the best indicator and there are others. The other thing finally to note about this is just the magnitude. The scale is in zettajoules, which is 10 to the 21 joules, doesn't matter, it's zettajoules. And roughly you can see it's about an increase over 50 years of about 5 zettajoules a year. Which doesn't mean very much to me anyway, but maybe it does to you. But the total amount of energy that mankind generates through nuclear, fossil fuel, transport, renewables, every other form of energy in the entire Earth, all anthropogenic energy generation is about half a zettajoule a year. So in other words, the Earth system is increasing by 10 times the amount, the energy in the Earth system is increasing by 10 times the amount of energy which mankind generates by all forms. So if climate is changing, it's hardly surprising. So this is one good indicator. Now there are some other measurements which have been made routinely for many years, and we have the so-called essential climate variables, and this is a set of 50 variables which the science community has agreed upon as being the things which are needed in order to understand how the Earth is changing. So it's things like surface temperature, but also ocean biology, atmospheric temperature, pressure, meteorological indicators, and so on. So these are basic parameters about the Earth system, but they're not necessarily the best ones for understanding or explaining what's been going on. And so we proposed that there should be what we call terrestrial vital signs. Surface temperature we have to take because we've had that for a long time. If we suddenly abandon that, then people will want to know why. An important one is obviously atmospheric CO2. That's what we've been measuring quite accurately now for about 65 years. And that's really what's telling us about what's happening in the atmosphere. Ocean heat content is another good one. And now I'll talk about 2 or 3 others of these which would be possible. One thing which I'm sure you've heard a lot about is the loss of ice from Greenland and the Antarctic ice masses. And if this is a study that was undertaken through the 2000s, between about 2003 and 2008, by a group funded by the European Space Agency and by NASA. It's called the Intercomparison Mass Balance Experiment. And it shows all the measurements that should be made by different means. There are basically 4 different techniques for measuring how much ice is in the ice sheets in Greenland and Antarctica. And they give you the different color measurements here. But you can see they don't give you a single correct answer, best answer. But this group took all of them, weighted appropriately, and gave the best history of the behavior of the ice sheet. And this is what happened in Antarctica. And these are the best measurements which have been made in Greenland over the previous 20 years or so. And if you plot these out more simply and you look at the consequences they have, so in terms of sea level rise, one way of interpreting this is when you lose mass, you increase sea level. So what did this have? This had the effect of giving about 0.3 of a millimeter a year sea level rise 20 years ago. And 10 years ago, that was about 0.95, so just under a millimeter. So there's been an increase by a factor of 3 or so over that period in terms of the amount of ice that's being lost and raising sea level. And since that time, it's gone up again. So this is a different measurement. This is actually a direct measurement of the amount of mass that's being lost, the amount of ice that's being lost from the Greenland ice sheet. So during that period of IMBY, the experiment was in the mid-2000s, we were losing about 180 cubic kilometers of ice a year. And in the last 2011-2012, due to this project called Cryosat, which has a British principal investigator, Duncan Wingham, it shows now this is a much better measurement of the loss from Greenland, and that's telling us that the rate of ice sheet loss has doubled between 2005 and 2012. So we get very good indicators here. Now, sea level is also something else that's a very important indicator, and it's particularly good because it integrates a number of other aspects of the Earth system. So you know that we have sea level rise. It's pretty linear. It's about 3 millimeters a year for the last 20 years. This is measured from a series of satellites, which you see there on the left. And we can even see where it comes from. So when the oceans warm up, as they have been, they expand, and that gives you the green line at the bottom of the thermal expansion. The other major component of sea level rise is ice being melted from both the Greenland and the Antarctic ice sheets, and also from land glaciers, which is very significant. It's almost as much as from the 2 big ice sheets. And when you add those 2 together, that gives you the red curve, but we can then measure that against what we see in terms of sea level rise, which is directly from the altimeters looking down on the Earth, and that gives us the black curve. So we have some confidence now that not only do we see sea level rise fairly precisely, we actually pretty well understand what's causing it as well. So this is a very nice indicator. The other thing that we don't often appreciate, though, is the fact that sea level isn't the same everywhere. And this is the differences in sea level rise in different parts of the world. And you can see that whereas the average is about 3 millimeters a year, which is the sort of yellowy ochre color, you actually have quite a wide range across the world of different amounts of sea level rise. So on the northwest coast of the United States, for example, actually sea level is falling with respect to the land. Whereas in Southeast Asia, I gave this talk once, and the previous speaker before me was the director of the Solomon Islands Meteorological Service, and the Solomon Islands is here, where the rate of increase is about 5 times the global average. So if we're talking about a 30 centimeter global average in sea level rise, in the Solomon Islands it's 1.5 meters. That's likely to be an underestimate. So they're very concerned about this, as you might imagine. This is a very good example of why satellites are very useful. There's the old joke which says that ships and in situ measurements measure everything nowhere, and satellites measure nothing everywhere. Well, this actually shows us how you are able, with satellite data, to get the changes and the differences across the world of a single parameter, even something as simple, apparently simple, as sea level rise. Another one, which is very important, is sea ice extent. You've probably heard about this as well. As sea ice waxes and wanes during the course of the year, as you'd expect in the polar regions. And what you see here is the minimum in 1980, it's shown in orange, and the minimum in 2012, shown in white, basically. So you can see this is the change in the annual minimum. This is the annual cycle you see. So it reaches a maximum at the end of the northern winter, about now, actually, 1st of March. And it reaches a minimum around the third week in September. And what we're looking at here is the decrease in the minimum. The solid black line is the average over the last 30 years. There is a slightly shaded sort of variability around that. And what I've plotted in color is the last 10 years, path of ice sheet extent, of sea ice extent in polar. So you can see we're towards the bottom end of this average consistently in the last few years.
Why do you say extent rather than volume?
Because this is sea ice, this is floating ice.
Yes, but the volume.
The volume is
thinner too, isn't it?
That's a much more complex question. In fact, it's only for the last 3 or 4 years we've been able to measure freeboard, the height of the ice above the ocean, free ocean.
That is correct.
But it's correct, it is important.
There's a very big distinction between ice that lives through the summer and ice that disappears during the summer, and the thicknesses are very different.
So you have first-year ice, multi-year ice, and so on. But the same cryosat satellite has been designed specifically to measure that. And this shows us what's going on this year. So it shows us up to about 2 days ago the distribution of sea ice extent for 2016. And so we're again running along the bottom edge of the range. That has all these have consequences, and this is moving into where Charlie will start talking. This is one of the examples of what happens when you have climate change, or one of the consequences. And this is the frequency of rain days in the Midwest United States in the 1960s, 70s, 80s, 90s, and noughts. So each of these shows 60s, 70s, 80s, 90s, noughties. On the right, it's where you have the numbers of rain days where the rain is more than 3 inches per day, 2 inches, 1 inch, and so on down to the left. So you have an increase between the 60s and the noughties of around 50% of the numbers of days in the Midwest when you have 3 inches of rain during a storm. So this is now beginning to see that this is not just a climatic phenomenon, but this is actually something which is quite relevant and important for us in our daily life. And to show why this is important, we can also go back to the idea of observations being where we are up until now, and models about where we might go in the future, and how best we combine those two. One piece of work which has just been published is about the sensitivity of plants. So this has measured the change in the vitality of plants in the last 15 years or so, 20 years, as a consequence of change, and as a consequence of different aspects of change. So this maps the sensitivity of global vegetation to 3 different driving forces: the lack of water, too high temperatures, or cloudiness. And so the areas where it's mostly blue is where plants have been under stress for the last 20 years routinely as a result of the fact they don't get enough water. Similarly, if it's red, it's because the temperature's been too high for them. So what you're seeing here is essentially a map of sensitivity, historical sensitivity. Now, if you couple this with a model which tells you where there's likely to be future lack of water, then you have much better information about what the sensitivity of the Earth system will be, not just about the climate telling you there'll be less water here, but this tells you a little bit about what the consequences of having less water will be in certain places. So this is beginning to hint at a way of being able to couple historical information and we start to get into the sort of Bayesian idea of prior probabilities of something changing with the future modeling, posterior probabilities that you would get from the theory. So at that point, that starts to move us into the transition from historical observations into future thinking, and that's where Charlie comes in. So I'll hand over to Charlie now.
So thank you, Stephen. And so this is Act 2 of the Stephen and Charlie show. And I must say that I've come at this whole topic. You'll see a repeat of Stephen's initial argument about temperature from a different point of view, but I've come at this from the point of view of the use of climate knowledge in decision-making, particularly in adaptation to climate change, and what it will take perhaps to improve that new use. So early on, I think a lot of people in the climate community complain about the use of global temperature, and it goes back to the earliest days when people saw an analogy with infrared radiation from a black body, and they thought it was a very nice way to communicate what climate change meant. And this goes back to the 40 years ago. So what has happened over the years, and I'm going to read this because we measure and compute a vast range of variables, as Stephen has indicated, and yet we focus publicly only on the one number that conveys the misleading impression that the world warms up uniformly. That increased temperature is the primary manifestation of climate change. And then we use this highly imperfect index of the rate humans are adding energy to the climate as our primary criterion. And I'm just going to show you some data that will tell you how misleading the global temperature concept is, and why, when it is used in the public arena, it creates a kind of cognitive dissonance that gets in the way of serious decision making. So let's see if I can move on to the next one here. Here we have, see, can we get this going? Is this going to start? Yeah. This is a big data display put together by Berkeley Earth, Richard Muller, University of California, Berkeley. More than 1 billion temperature measurements taken on land over the last 2 centuries. And at the top you see the number of stations in years, the date, the percentage of the Earth's land that has been covered, and here the color scheme will give you the difference between the long-term average at each location. At the bottom, the little red golf ball down there, that is the global land surface temperature, the average of all that you see. All right, now here we are, about the U.S. Civil War is just about starting here. And so it's going up and down. This is as good a data as we're going to get about temperature. And now it's 1880, as time of maximum fog in London. Turn of the century coming up, 19th, 20th century. Well, here we are, about the First World War now. And then there's a sort of a long stationary period, quasi-stationary on land. Notice that the temperature, average temperature, goes up and down, and in any region the contrasts are much larger, much larger. So now we're coming up to the era. Now 57 is when Dave Keeling discovered the carbon CO2 accumulation in the atmosphere at Scripps. There was a long period of time in which the temperature remained constant because air pollution was counteracting greenhouse warming, and beginning about 1970, this global temperature started to increase. So there we are. This data display ends in 2009. I'm sure they've updated it, but I haven't. So what do you conclude from this? Which of you has ever experienced global temperature? The best you can hope is maybe you can remember a hot summer. Right? So when people think about temperature, the public thinks about temperature, they think about the temperature in their region and what its behavior has been. And this conditions their readiness to support serious decision making. You will notice certain places here where it didn't warm. The American South, the hotbed of denialism, climate denialism in the United States. Siberia, they're very happy. They're looking forward to its warming up. So the global temperature is not a very helpful guide to people when they think about what they must do in their region to adapt to climate change. Now, more than that, global temperature has gotten us, we scientists, into hot water. And I'm going to describe that in a minute. And you're going to see it's because of the way we have to do business and the use of the data that we have. The first time we got in trouble was in 2009 when some people, presumably in Russia, hacked the email conversations at the Climate Research Center at the University of East Anglia, where they caught informal discussions about how you marry together instrumental temperature measurements and the various temperature estimates that you get from proxies. It's a matter of judgment. And it was thought that they bias. It was accused, and the accusation emerged 1 month before the failed 2009 meeting in Copenhagen, that it was thought that they had been biasing the data. Okay? That's not the first time. It's happened again. Here's this similar data for that Stephen showed. This is even somewhat more modern because it appeared on Wednesday. And so what you see here is an extraordinary plot that was put together by about 20 people that shows the 3 major data sets that have been used in dominate the IPCC thinking and the results of climate models. And this is their confidence range of the models, and the average of the models is in the black line. And what you see is that until about the year 2000, models and data agreed. Okay? Following that period of time, beginning about the year 2000, there is this hiatus in warming that all 3 data sets agree to, and the models disagree. This has been a godsend to those people who oppose action on climate change. And if you were to look at the discussions in the American Senate, for example, they would say, why do anything? The climate, they've got their models wrong. They're predicting global warming, and the temperature hasn't changed at all. So why should we do anything? It stops initiative in its tracks in places where it has been used. Here was something that happened here in the UK. So here's a newspaper article that pointed out that there was a time in 1998 and a time in 2012 when the global temperatures were exactly the same. Now, this has been a real problem. How is this problem generated? It's from the way we manage the data. It's a process that the climate scientists call reanalysis. I suspect it has its other names in other areas. But what we have are gaps between sparse data of different types that are taken at ill-assorted points, far from one another in space and time. And they have to, in order to get the plots, you have to fill them in with using the multi-parameter models that are constructed from other data and deterministic calculations, if you can do them. So the results of such an analysis depend on the accuracy and the completeness of the measurements, the realism and precision of the models, and the rigor of the statistical efforts that are used to merge model and data. And the models are embedded in the data, and vice versa. So this means that progress is recursive. Improvements in observations and all these other things produce new results that, once again, are then treated in data as data in other analyses, and the progress is circular and sort of reflects the culture of the science of the time, if you will. Okay? Now, I bet you haven't heard about the second law of reanalysis. As knowledge improves, the data change. Same data. So this is what happened. There's now a controversy within the scientific community because NOAA did a reanalysis of largely the earlier data here. They looked at how ships and buoys they found a bias in the measurements made on ocean temperature and ships and buoys, and they included later data, and out they came with this plot that said the hiatus is not there in the surface temperature, right? So this aroused political suspicion as well, and in fact, Congress has hauled NOAA and its scientists to testify and to try to explain why, as many people think, why there was no tampering of the data to reach a politically correct conclusion. This is how this knowledge is getting used in decision making. So that's the hot water that we've gotten into. So what's the moral of this story? It's not enough to be right. Right now, many of you live in the UK and Europe, you're thinking attribution is settled. We already know why it's happening and who's doing it. You think that the denialist phenomenon is over, except in the US. And you also think, as is true, that we have unusually crude ways of displaying political conflict. Okay. But I have to caution you. What is shouted loudly in the US may be quietly held elsewhere. And this leads to unresolved cognitive dissonance that produces resistance to taking action, conscious or unconscious resistance. It slows down your willingness to make a decision. So trust is the coin of the realm. And of course, we've known since IPCC was founded in 1988 that we have a responsibility to build as much trust as we can. And so could we have done a better job with temperature? Now this is again where I will go over the same area that Stephen has gone over. Why do we let the world rely on temperature? And as he's pointed out, the surface temperature atmosphere involves 2% of the energy, so the heat content of the ocean is a much more fundamental indicator. And I'm going to tell you, because Scripps invented this system, I'm going to tell you how we actually measure the heat content, and it's an extraordinary international project. The first thing to realize is that Russ Davis invented these little floats that can change their buoyancy by moving hydraulic fluid up and down in this, so that they can float at an arbitrary depth depending on the pressure. And they carry instruments, of course, here. They descend to depth. They float for about 9 days at 1,000 meters, measuring what has never before been measured, which is the circulation of the ocean at depth. Then they dive deep and take a vertical profile like this, send their information back to a satellite where it is collected in France and in northwestern United States. It's a great international project. There's close to 4,000 floats out there. A lot of data. And of course, these dots are pretty big, and actually the floats are about 200-300 kilometers apart. So no matter how much data it is sparse. And it is sparse in a serious way because a few hundred kilometers is the scale of eddy transport in the ocean. But nonetheless, it is a vast improvement over what we had before, and in the last 15 years it's collected 3 times more data than we ever had about the conditions underneath the ocean since they were first made by Challenger in 1870-something. So now there's about 1.5 million vertical profiles, times when it was collecting data on density, temperature, salinity, and so forth on its rise to the surface. And if you reanalyze all of this data, using the information that you have about the heat distribution and the circulation that you get from the different displacements between where the floats go down and where they come up, then you'll get, and this is a recent one that came out within a month or so, Lawrence Livermore did a very big job of looking not only at the most recent Argo data in here, but did the best it could with historical data. And what they have found is that during the hiatus, half of all the energy that has been added to the ocean system has been added during the hiatus when the surface temperature was constant, roughly. And we understand that because much of what is happening, there are other measurements from the Argo system that show that burial of heat to depth started in a serious way in the year 2000. So here's a question about scientific good behavior. What would have happened if ocean heat content had also been a benchmark for climate modeling? Since global surface temperature attracts so much attention, the modelers will do everything they can and adjust all the internal parameters, of which there are many within their models, in order to get the surface temperature to come out right, as it did most of the time before 1998 in that plot. But suppose they were told that you really ought to get ocean heat content and surface temperature jointly. Suppose they had to optimize their choice of internal parameters according to those 2 criteria. Now, Would they have done better in separating the global warming signal and the El Nino signal, which what we think is the reason that temperature remained constant? The models don't get it now, but they might. And more than importantly, and this is the one that we are going to emphasize in the vital signs argument, would the decision makers have looked at both temperature and ocean heat content if the modelers had done so? So this whole episode is troubling, very deeply troubling. An important policy debate has been hostage to delicate aspects of reanalysis. Reliance on a single indicator is tricky. And we know now that had ocean heat content been as visible as global temperature, we wouldn't have had all these ideological arguments that were used to slow down decision-making on climate. Of course, the heat content data is fragile. It has its different fragilities, but every data stream of this length has to be sutured together. Every data stream is sparse. They have to be sutured together, and they all have their fragilities. So the only answer to that is to use multiple data streams and refer to them and ask whether, in general, they point all in the same direction. And you look at the balance of evidence. This is, after all, what people do when they're dealing with other complex multi-parameter nonlinear systems. International banking, central banking finance, the status of the economy, even medicine. Multiple indicators, and you look at the consistency of the picture that is drawn by the sum total of them. So it was this kind of thinking that encouraged David and me to write a paper that attracted a fair amount of attention, in which we argued that really, and this was before the climate negotiations, they really ought to ditch the 2-degree goal as a long-term planning requirement. And we had several regions. I went to David and told him the global temperature was misleading, that we were trapped in this El Nino, La Nina situation, and it was a misleading indicator of how well people would be doing on climate change, and if they continued to use it, eventually the negotiators would be seen, they would not be seen as trustworthy. And we both agreed that it looked highly likely, unless some heroic technology development comes about, it looks highly likely that we'll go through the 2 degrees by 2050. It would require an amazing amount, a huge deployment of carbon removal technologies which have never been proven. And then finally we all agreed that business as usual is unacceptable. I think everybody knows that. But there was when the negotiators in 2009 chose the 2-degree goal, they stated it was a scientific result, that was the threshold of dangerous climate impacts. And they asserted this as a scientific conclusion when in fact it had not been analyzed. And the analysis came later, and the best people could do was to conclude that 4 degrees was unacceptable. So we've put everything in context. We've done about 1 degree now. We expect, IPCC expect a 0.5 degree by 2030, another 0.5 degree. So this is how we got to the question of multiple indicators. Stephen read this article, we joined forces, and we're beginning to work on trying to get the communities to do those things that are required to build confidence, sufficient confidence for decision-making in the indicators that we think we can produce. So now I'm going to talk, at the end of this, I'm going to talk about another dimension of the climate decision problem, and this is the issue of climate risk. What risks do we run in the future? So first of all, I think it's worth pointing out that at Davos this year, they declared that the failure to mitigate or adapt to climate change is the largest single threat to the global economy. It's the first time that it has risen to that level of salience. I think the other point that's worth making is that scientists don't make the decisions on climate. We don't. It's politicians and business leaders. And they respond to risks, to things that the public cares about, and not the abstract threat of climate change. To us who are immersed in the data, climate change is not abstract. It's tangible. We see it every day in our computers and in our environment, but nobody else sees it that way. So, in addition, there was a very fine report that was generated last year on behalf of the UK Foreign and Commonwealth Office, in which they looked at climate change not so much as a scientist would, but as an insurance company would. And they asked a different set of questions. What kind of risks does the UK run as a country? What do other countries and regions run? And they made an important distinction that I think I would like to introduce here. We have introduced vital signs, which are actually empirical indicators of ongoing change. They then made a serious distinction between direct risk. Can I predict ecological change, as Stephen suggested, from knowing the changes in climate? And then they asked about systemic risk, risk to human systems, in which the question, the query-based outcome probabilities, what is the worst thing that can happen? What's the probability that there's an existential risk to my endeavor? So earlier on, when I was thinking a bit more about adaptation and what was required to think about it, I produced an idea that there is actually a knowledge cascade, that the way knowledge will be used in adaptation decision-making. And the way to think about it is, suppose I have a climate model. I have all 40 or 50 climate variables. I know what's happening there, and I know it at the global system. But I need to know what's going to happen in the upper layers to the large weather and open ocean systems before I can predict what will happen to the regional geophysical systems, ice fields, watersheds, and the like. And I have to know these two things before I can figure out what's going to happen to the ecological systems. And the humans are sitting down here at the bottom waiting for this knowledge to come down and be connected one to another. And of course, what they recommended, and I thought it was very profound, was that you just jump from the region of vital signs here and jump over the direct risk question in order to prompt some timely decision making, and then just ask about systemic risk to agriculture, to forestry, to disaster response and civil infrastructure, food security, environmental security, migration. All of the issues that humans care about are here. So, 3 different kinds of indicators. Now, in that diagram, there is a common challenge. If you want to connect the items in the different levels. And the common challenge is to find traceable pathways that connect independent knowledge domains and ontologies. And there's a collection of methodological issues, some of which I referred to when I discussed reanalysis. Sparse data, inhomogeneous sampling, incommensurate data types, no specific causal connections, empirical bins, arbitrary formats, statistical outliers, important, use expert advice. Those of you who are more expert than I see that all of these things tell you that you cannot use a deterministic calculation to get between levels, but you could use big data Bayesian analytics. And so I believe that there's an opportunity now for those people who think in that way to make a significant impact on the way knowledge cascades down from the global level, if you will, to the people who need it to make key decisions. So here's another question for you. Think of the scale of the adaptation problem. How is the science, policy, and technology community, as we know it, is pretty small. How is it going to develop the capacity to serve millions of decision makers in all the regions, dozens of industrial sectors, hundreds of ecologically distinct regions, thousands of communities with different cultural, economic, and environmental characteristics? So the only way that the influence of this community can be amplified and to reach all of these users is clearly to create some climate-smart infrastructure. We're getting into the speculative area now, so you don't have to trust everything you hear. But one of the things that is important for smart infrastructure is you need a guide to the information jungle. Who are you going to trust? This whole temperature story tells you of the necessity for trust. So who are you going to trust? Well, one of the things that has to happen is that the scholarly community works with the IT community to build annotated search engines where the knowledge that you find has a pedigree and can be, and degrees of its utility are emphasized. So in 2012, in a series of thinking about other things, we did ask at the end of our 2 articles here, listed at the bottom, a question about knowledge action networks, how you connect knowledge to action. So shouldn't we be thinking in advance of an always-on social and information network that provides decision-ready knowledge to those who hold the responsibility to act, wherever they are at times of their choosing? In other words, why should we wait for IPCC reports to come out every 7 years? If the information's any good, let's use it right away. Shouldn't we prepare the social infrastructure in advance, the policies, the governance, the institutions, the financing that we will need because we will know we need to knit climate knowledge and action together. So it's a kind of hierarchical system. I think everybody understands when they think about these problems that there really are 3 levels in which you have to be working. I think globally. There used to be the mantra, think globally, act locally. I just added assess regionally and put that in the middle. So there's a kind of geographical cascade or a connectivity, human connectivity cascade, as well as a knowledge cascade. And this gradually led to the idea that what we really need is some kind of global knowledge action network, smart infrastructure, smart IT tools embedded in a system like this, with that kind of structure. So ultimately, what is it that we're trying to do? Can we use the tools at hand, observations of space and ground, demographic, economic, societal measures, big data, statistical techniques, numerical models, and modern communications, all the things that mark the beginning of this century of science, can we use it to produce global continuous awareness of the nature and evolving risks of climate change? I think if the problem unfolds as we think, we eventually will have to get there. And the question is not that, but when? Are we ready to start now? And where did all these ideas come from? I thought I had them myself. But in fact, I recall now, as a very young man, a dinner table conversation with the great physicist and polymath Philip Morrison from MIT, who was visiting UCLA, and we held a dinner party at our home for him. And during this party, we were all young faculty, very senior guy, and one of the young women there asked him, well, Professor Morrison, you know so much. Can you tell us what you think will happen in the future? So he said, well, you know, look, your husband is at UCLA, and where we have first interconnected the computers, got them to play well together. He's working on that. And soon there's going to be a worldwide network of connected computers. And we will first use it to manage global finance. But the expansion of economic activity that induces this great efficiency of financial decision-making will create so much pollution that the system ultimately will be asked to manage our economy and environment in harmony. And people will want day-by-day, minute-by-minute adaptive management for which they don't have the patience or the skill. So they will decide to connect their environmental sensors directly to that computer network. And at that point, he argued, they will have created a planet that's aware of its own internal processes, a planetary consciousness. And that, he said, is what will communicate with similar entities across the galaxy. So I'm pretty sure we're going to head in that direction, and we're on the way to building his planetary consciousness. We're thinking that we're going to use it to help us diagnose the ills of the planet, but it may decide that we are the problem. Thank you.
Thank you very much, Charlie and Stephen. So Charlie, why don't you sit down here,
Yeah,
and I'll stand up and face around a bit and spot people who'd like to ask a question. So if you'd like to ask a question, please raise your hand. If there are a lot of hands, I'll start to make a queue. But Jane, would you like to go first?
Yeah, thanks so much. Really very wide-ranging, very, very interesting observations altogether. Thanks very, very much. So you cast some doubt, and I think now I see absolutely why, on the 2-degree target that we've got built in the Paris thing. Would you be equally uneasy or sceptical about 450 parts per million or so forth of CO2 in the atmosphere, and that kind of goal as something for planetary stages and so on?
I think,
set their eyes on?
well, first of all, I'm going to talk to you about a technicality. The 2-degree temperature that they're talking about is the long-range asymptotic temperature that will be achieved if you should manage to cut our carbon emissions. And so that 2 degrees is in the class of long-range asymptotic temperatures, but it is not in the class of contemporary temperatures. So, but any temperature, long-range temperature measurement is almost directly proportional to the additional amount of CO2 that we can put into the atmosphere. And that is a useful concept, because it tells you the world has a certain carbon budget, and we have to figure out how to divide it up. So there it is useful. But what's about to happen is something different. Temperature will be used in a different way, and there I think it's very misleading. The Paris Agreement specifies that every 5 years, governments get together and they review what they have done or not done, and they agree on a next round of emissions. And they, in other words, they have started off and at least enabled an adaptive management approach, which is the only one I think you can take in this area. And so every 5 years, the governments are going to get together. And most of the time, they're going to be worried about what the other governments have failed to do. But the bottom line for them and for the world and the public is whether or not you have actually improved the climate, and also at that moment, whether your climate indicators communicate to you a sense of urgency about the next round of decision making. And so what we would like to see happen is that the UN, Stephen is working a bit in this area, the UNFCCC actually ask for a basket of small number of indicators that all people can look at that would give you a more objective view of the climate, and one that's less, it's not hostage to the details of a particular analysis procedure. And that's the sense in which we think that you should not judge progress toward the goal by the contemporary temperature. But you can judge it by the total emissions that people will be putting out. That's a complicated answer, but that's right.
I just add to that, the useful thing about temperature is that over a small linear range where we are today, the increase in temperature is directly linear, pretty well, the amount of additional CO2 we put in the atmosphere. So you can say for 2 degrees, that's equivalent to 750 billion tons of carbon into the atmosphere. We've already emitted 500 billion tons. Another 250 billion tons to go. An engineer or a scientist going to Paris would have said, well, the question's very simple. You can all, between you, emit another 250 billion tons. It's up to you to decide who gets it. And that's what they tried to do in 2009 in Copenhagen. It failed miserably. So they started from the other end of the problem, which is to say, what do you think you can do? So it was helpful, and this is where I'm slightly less cynical than Charlie, that the 2 degrees was useful. It served the purpose at that point.
Oh, we agree. It served the purpose of focusing the negotiations.
But the question in the future then is, are you going to judge your success as to whether you stick to 2 degrees or some other number? Or are you going to judge your success as to, by much more directly applicable indicators, the way the world is changing? It's much more helpful. I mean, temperature really doesn't make much difference. You don't notice if the temperature goes up half degree or even 2 degrees. But you would notice if your agricultural production dropped by 50% in a certain area. That would have a direct impact on people around you. So really what we're trying to do with these indicators is to find ways of providing information to politicians which, if they were aware of that, and if they were to act in the right way, because it's always a very dangerous assumption to assume that given the right knowledge, politicians would do the right thing. But assuming that they would, what information can you provide to them which would allow them to understand whether their policies are going in the right direction or not? And it may be the temperature is actually almost disconnected from reality, in the way that Charlie's talked about today. But at least for the moment, it's serving a purpose. We give too much credence to it at our danger, at our peril in the future, though.
And the other course is that how do you know that the 2 degrees is the right number, or 250 billion tons is the right number?
I'm more confident about the 250 billion tons than the 2 degrees.
Yeah.
I was wondering whether you had any confidence at all that 450 parts per million was a sensible CO2 equivalent. It was a reasonable. Or I mean, do you say we should get back to 350?
I only know what I read, and there's a very persuasive report from Potsdam that looked at an emissions profile that would lead to 4 degrees by the end of the century. And there it was pretty clear it was unacceptable. We're at 1 degree, we're looking at 1.5 within 15 to 20 years. And a lot will depend on how we reduce emissions after that. The other thing the treaty did not do, by the way, is, and it was not possible for them to do, the decisions taken there will affect the long-range climate, but they will not stop the climate change that's in progress because of the energy that's already buried in the ocean, some of which will be returned, and because the carbon in the atmosphere, once you put it in, lasts 100 years. So there's this great inertia in the system, and we are going to, and our children are going to be victims of what we have already done. And that climate change is coming soon, and there's precious little that we can do about it.
Okay, it's quite a forest of hands. I'm going to, could the people over there please keep your hands up, and I'll make a queue. But I've got 2, Sean and then Richard. Sean.
So, Professor Briggs' last comment preempted this a little bit, but I'd be interested to know a little more on it. Let me speak up. So, David King, who was mentioned here, spoke 2 weeks ago at a company with scientists, and at the end of that talk I asked him what he was most worried about, and what he said was that this wonderful momentum and political will towards making progress on climate change, that dissipates. And it seems like there's a delicate situation to be managed here, in that you made a very compelling case that 2 degrees is a very, very flawed target to put all our eggs into, yet it does have a lot of political will and support for it. And a skeptic might be, or a critic might be concerned that from the outside view, the climate community seems to be sort of eating itself if it's attacking these targets. At the same time, I can see the argument that if you stick to a flawed indicator, then you're going to run into problems anyway when the analyses just break down, or where we simply aren't measuring enough of what we actually care about. But it seems like a very tricky one to me.
The question is, if you will, the misuse of the temperature concept. It's perfectly useful to define a long-range goal because it is equivalent to carbon burden. It's when you use it as a measure of your progress that it is going to present a political risk. For example, think of the hiatus, for example. That produced disillusionment. So if you don't have an accurate picture of how the climate is changing, and if, for example, the impacts of climate change will multiply regardless of whether the temperature, regardless of what the temperature does, which is what we're seeing now, there's risks of disillusionment on both sides of that issue. And so the real question is its use. What do we use to tell people, the general public and high-level decision makers who don't exercise their own analytic tools, what do we tell them about how the climate is doing? What should they listen to and believe?
You've actually made you encapsulated very precisely a real problem that we have, which is that you finally got politicians to think about doing something by talking to them about temperature, and then the next thing you tell them is, by the way, you shouldn't think about temperature. Yeah. So it's not very smart, and so we have to say the second very quietly amongst ourselves.
Yeah, and then I think they gradually just, I believe that if you build vital signs and you declare them to be official, you won't get any place. But if you let them start developing them and let them permeate through the system and present them to people along with the temperature, and gradually, one by one, I think they'll begin to understand. The analogy is with medicine. It's rather glib, but you can, if you think about medical vital signs, blood pressure and the like, I'll just point out you can have cancer without running a temperature.
Richard.
Oh, thank you for a very informative and comprehensible talk, both of you. I quite liked your idea of the knowledge cascade, starting at the very general abstract level and working down to the regional level. It seems to me that when you get to the regional level, there's another study that we need to engage in, and that is the study of human well-being. How much people can cope with, what they can put up with, what they're willing to live with. Sean mentioned Dave King's talk to Coffee for Scientists. One of the things he emphasized is the difficulty that we're going to have if we continue to eat meat at the level that we are eating it and continue to consume it at even greater levels. It seems to me we need to look at well-being in terms of diet. What are people willing to cope with, and what will happen if they don't?
I think the Paris Agreement states a global agreement for the first time that business as usual, including that, is unacceptable. And they also create another goal, which is to move the time of peak carbon forward, accelerate everything you're doing. So if you do that, that actually is something that, for example, is to the advantage of the advanced countries, because they're calling for a global deployment of the technologies we have. But at the same time, it calls on every institution in society, including universities, I think, to re-examine what they're doing and ask, can we accelerate the rate at which we're reducing carbon emissions? That is a fundamental question.
But I think I'm more limited in my ambition. I'm very happy if science is able only to predict precisely what is going to happen in the future and get it right, and let somebody else worry about how they're going to react to that. But I think a real critical point, this goes back to the issue of temperature and vital signs. What we would ideally love to have is some indicator, I don't care what it is, if only we could find one indicator which would be a very precise measure and would reflect precisely to politicians exactly the state of the Earth as it is today. And temperature is not the one that's been assumed up till now, and it's not the right one. But until we've got a better one, let's not be too suspicious about temperature. But what we're talking about is how do we understand the things which are actually relevant to policy. Temperature is not relevant to policy per se. Food production is relevant to policy. The numbers of people who are dying as a risk of increased disaster, risk exposure. Those are the things that really matter to the policy people, and that's why the outcomes are important for mankind. Temperature is a sort of an arbitrary concept. It doesn't really matter, but it's the consequences with all the changes in climate, including temperature as a byproduct, is all the other things which are important. And so how can we find a way of measuring all those other things in a way which is sufficiently frequent and sufficiently precise to provide that information to society for it to make the decisions itself. We're never going to be able to tell them, the society, they should stop eating meat. But if they come to that conclusion because they can see what happens if they don't, then that's smart.
The vital signs is only the beginning. Just getting people used to a richer set of indicators that we think might produce a more objective view of what's happening. But if you really want to affect decision making, then you're going to try to develop much more precise risk indicators. There will be pathways, I trust, that will connect the broad sort of set of vital signs. We're in this kind of climate state, and therefore we can expect that to happen. But it's really the risk indicators, the ecological risk and the risk to social systems, that are persuasive. And the flow down, I mean, all of this is going to have to be communicated not in any linear way, but in some very large and climate smart network.
You, sir.
I like the idea of the basket because our state of scientific knowledge just isn't up to this ideal of a single measure. There's too much uncertainty. But one example that might have some political traction is, of course, weather extremes, and you mentioned them. Yeah. And I hope that's in the basket. One of the things about that is it will change because the computer modeling is only just beginning to get nearly good enough to capture them. Yeah.
James Hansen has invented a measure that I like very much. And it is a big data measure because you look all over the Earth and you look at where you have enough data, basically. And the one area where you can do this is temperature. And then you look at the duration and the area over which the temperature, let us say in a heat wave, or for that matter, a cold wave, deviates by 3 standard deviations from the local climatological mean. Okay? And that area changes with time. And in one of his papers, he showed that in the 1960s, that area was, this measure of climate variability, was about a couple of percent. But it's now up to 10 to 12 to 13%, depending on how you measure it. So that is a measure of climate volatility in extreme events. And something like that is useful.
And needless to say, the models do not capture that because they're not good enough yet to get the extremes, especially rainfall.
There are 2 problems. One, they're not sufficiently small scale. I mean, the great improvement in futures will be to have regional scale models as opposed to global scale and seasonal variability included. So then you begin to say what's actually going to happen in Eastern Europe as a result of this, as opposed to what's going to happen in the world. But you need to couple that with all the things that are on the ground, because knowing extreme events is not so important if it doesn't affect anybody. But you need to know, for example, if you're managing the upper Rhine hydrological basin, then you want to have a regional prediction of rainfall for the next 20 years. But you need to know what the demography is, where people are going to be living, what's the local sealed surfaces, how is the hydrology going to operate, what the land cover is going to change. That gives you a model then of what's going to happen within the particular basin that you're interested in. And that can tell you how the people in that basin are going to be affected and how agriculture will be. So that's where you get down to the real downstream end, which is what are the consequences of climate change going to be in terms of how much better off is this particular section of the population going to be, or worse off. That's where we need to go with it.
If you think about this question of extremes, I think if people who think in the frequentist way about statistics will say it's awfully hard to predict long-tail events, and it certainly is. On the other hand, you can do what you can do, and on a probabilistic sort of Bayesian approach, you can take whatever data you have and then see what kind of answer you get to a question like, what is the probability that something will happen? And at certain points, I think it will work out where there's enough data. And you'll be able to make a toy model that will give you some idea of how the long tail evolves as a result of the main driving parameters of whatever you choose. And that you can verify in a data-rich region and port it to a data-poor region and just tell people this is the best we have. And so I think that one shouldn't be entirely defeated by the long tail problem. The other thing you can do is actually consult expert committees and try to reach some kind of judgment and fold that into the analysis, and you'll get some sort of definable, traceable pathway. Not necessarily accurate, but one whose every step can be illuminated to anyone who cares to doubt the origin of the statement.
I like the idea of having a basket of indicators, because it seems to me that the key issue is about trust. And you don't need to say, well, we messed up on temperature, so we're going to try another one. You just say, you don't trust us? Well, let's try a basket. And let's see if those all fit. The other thing you can do, give temperature.
Oh, yeah, of course we keep temperature.
Of course we do. There's other measures which may be particularly useful to policymakers, like CO2 levels in the atmosphere. Presumably that responds relatively quickly. I think you might even be able to start reducing regional CO2 emissions. But it's just like the RPI. You might even say that different parts of the world might choose to have different elements in their basket. If you are the Netherlands, you might be more sensitive to sea level rise than if you were Nepal. And I think also, maybe not just CO2 in the atmosphere, but there may be other indicators like methane or soot. Because I think the psychology of it is going to be important. We need trust, we need urgency, but we also need hope.
If you embed a lot of this knowledge in a smart system and give people traceable tools to analyze it, then they will build their own regional assessments themselves from the knowledge, and that in itself promotes trust.
Yes.
And so we're going from a way in which we're trying to get away from authoritative top-down pronouncements into a responsive knowledge management system that helps people construct their own decision options. I think it's the best way to say it.
There are two roles really for different baskets. One is the sort of rather trite but historical one, which is communication. So people do really understand what is going on. Something is happening and they can see it's happening. It's not just an argument about one parameter. And that's sort of trivial, but it's far from solved. The more useful one is the future projections of those parameters. As you say, for the Netherlands, sea level rise is particularly important. For others, less so. And that's then concatenating all the different types of information, the demographies, the way the populations change, the way that people live near the coast than they used to. Sea level rise, but coupled with storm surge, which you get from increased violence and velocity of winds. So all these things are important. So you have parameters which are about the numbers of people affected by. And then you get into the realm of insurance, and these people are really good at it. They've been doing it for a long time. So the reinsurance industry in particular is very happy to understand what's going on with these long-tail events. They want to know what's the 1,000-year return, what's the 500-year return. And they don't say, well, it's unlikely to happen. If it was unlikely to happen, they wouldn't have a business. It's unlikely, but it's going to happen sometime. And that's why people insure against it. Mm-hmm. So I think we have a lot to learn from the way insurance actuaries calculate.
And that was, I think, the profound thing about that most recent report, was they pointed out that the scientists think about risk in a different way than the people who worry about risk do. Gosh, I had a thought, but I lost it. So let's have another question.
But this sort of frequency of return, there's a very nice point was made at that meeting by Emily Chopra from the British Antarctic Survey. The 2003 heat wave event in southern France, which killed about 30,000 people or thereabouts, was a 1 in 100. Given the statistics that we knew about in 1990, was a 1 in 100-year event. Given the statistics in the world system in 2005, it was a 1 in 50-year event. In 2015, we know that that's a 1 in 5-year event. Mm-hmm. So historically, one can actually revise one's knowledge as well.
And the Potsdam report will say, for example, if you reach 4 degrees by the end of the century, that there will be entire regions on the surface of the Earth where the average summer temperature exceeds the highest ever achieved in that region in the 20th century. So that every day of the summer will be a heat wave in those places. There's another report that looks at the conditions for sustaining, temperature conditions for sustaining life. And we know there are areas such as the empty quarter in Arabia where it's so hot that nothing lives naturally. And so then they can actually predict, using those conditions, they can begin to estimate at what point will how will that extremely arid and hot area, how will that expand under climate change conditions? So.
Okay, you're next, near the back there, yes.
Thank you for the very talk. So it's a little bit a basic science question, no background in biology, but physics. I was wondering if you could elaborate on the relationship between energy and how kind of temperature increases. You said that the ocean is taking up 90% of the energy, which into the system, and the land's only 2%. So what percentage of those are responsible for the 2-degree temperature increase? And how do you measure ocean heat?
Well, you measure, the last one is easy. You measure ocean heat content with the Argo floats. So you have thermometers that go up and down in the ocean.
It's very
temperature.
It's very simple. If you know the temperature, the density, and the salinity, you know basically the equation of state for water. So as the float arrives, it measures those three things. It computes the heat capacity, and then you get all the energy. You track all the energy from the bottom of the from 2,000 meters to the top, and that's right now the ocean heat.
You have to remember the difference between temperature and heat.
Yeah.
If this room is full of air, and you want to warm it up, you can warm it up with a couple of radiators in an hour. If you fill this room with water, it will take you like 2 weeks to warm it up. And that's essentially why most of the energy goes into the ocean. If it's at the same temperature as it goes up, then most of the energy goes into the ocean. So that's where the energy goes. It's not where the heat goes, but it's not where the temperature rises.
Because I had a question. There are no oceans, and so the ocean wasn't absorbing any heat. What kind of temperature increase?
I think the oceans have a much more fundamental influence on our climate than simply absorbing energy. They also conduct it around the world and everything else. So I think you would be in a different situation. I think you can regard that as being a perturbation of the system that we're in, mildly different. It would be quite different.
I was just wondering if you're familiar with the, I think it was about in 2009, some scientists led by Rostrom developed the planetary boundaries, and so they were the same point of we need a number of indicators to look at the sustainability of the planet. I was just wondering how that links in with your vital signs indicators and whether or not they're aligned, or if they're not, the indicators that they're proposing aren't actually the indicators.
I think if I remember correctly, what they were looking at was not so much what are the parameters we can see about the Earth system, but what's the carrying capacity of the Earth in different directions. So what happens when we get to, what are the critical boundaries beyond which we exceed sustainability of the Earth system? And they weren't necessarily physical indicators of the physical system. They were sometimes biological indicators, and sometimes they were social indicators. So they're a rather wider mix of different
See if we can go back.
They were carrying the capacity of the planet, characterized in a number of different ways. Whereas we've been trying, certainly what I was showing, and then sort of became a bit more speculative, is really based on physical measurements about the Earth system, the physics of the Earth system, with a little bit of biology throwing indications.
I'll answer this is the Stephen and Charlie show. We each have different answers. We came at this different ways. Planetary boundaries are very hard to compute, right? And to assert that there are some is different than asserting you know where they are. And at the present time, I don't think that the planetary boundaries that we are encountering at the moment are involving with, say, the complete removal of the ice shelves and functionally irreversible changes in elements of the climate system. And and these are this planetary boundary question is the scientific version of some of the systemic risk issues that we're looking at for human systems. I could have said systemic risk to the climate system. At what point do we get irreversible deleterious changes? And I just want to draw a distinction. The vital signs give you and the public and high-level decision makers a better way of looking at our general progress. These direct risks are the ones that we can compute are incremental risks. The climate changed a little bit, and we saw a little bit of change. And these don't help us find planetary boundaries. So once again, when you get into this approach of systemic risk, you have to, and I'll amend this diagram, where are the planetary boundaries? It's the same kind of question.
As a corollary to that, maybe we shouldn't think about planetary risks in the sense that the planet's going to be quite happy it'll be there. It's just a question of whether we're there as well. And Rockström was mostly about the carrying capacity in terms of humanity. What sort of conditions that humans can continue to exist in the same sort of numbers that we have now. But we do risk, and this is the sort of unknowable, where you go past some mathematically catastrophic point in the system, where you have positive feedbacks. And there are that's the really difficult thing about this. It's sort of, yeah, it's predicting the unpredictable. And that's where there are real concerns. You may suddenly go past some point where you are no longer able to retrieve the situation before. That may be happening with the West Antarctic ice shelf at the moment. Not quite sure. Beginning to show some signs of it. It could happen in Greenland. It's not going to under the current conditions. But the Greenland ice sheet only exists because it's 4,000 meters high. If you removed it, it would never grow back again, not under current climate conditions. Because it only exists because it's so high that snow falls at the top. So basically it's a fat pipe. Snow falls on the top and it slides out the side of glaciers and into the ocean. And then precipitation fills up the top again. So the total amount of mass is reducing, but not anything like as much as the amount of ice that's being lost. If you were to stop precipitation at the top, in other words, if you were to lower the top of the Greenland ice sheet by 1,000 meters, so it was no longer snow, but it was water, rain, then you would just get a runaway decrease in ice sheet. That isn't going to happen in today's system, thankfully. But that's a typical. Well, because the loss isn't sufficiently rapid at this point to be able to reduce the altitude of the height at present. It's actually the sand is growing.
It's a good example of where the climate's not good enough, because we don't know the snowfall. We can't do the storm tracks, and we don't know the snowfall rate.
We don't know it as well as we should. We know the we know the altimetry of the centre. We know what the shape of the centre is doing, but it's very poorly done. I agree.
The thinking about thresholds at the moment are basically existential risk to climate and ecological subsystems of the whole. There is one planet that has crossed that boundary as a whole, and that's Venus, where there was an irretrievable change in global climate.
Oh.
One of the parameters that's of great interest to politicians is future global economic growth. Okay, one of the parameters of great interest to politicians is future global economic growth. David King makes a point in a comment piece in Nature this week that economic models, as they relate to climate change, are just very, very bad. Do you think that following this kind of line and taking quite a granular approach using big data techniques, you can get a better relationship between future climate change and future economic growth?
You might be able to do better with the cost-benefit ratio. And the reason is that if you could actually compute these impacts on a local and regional basis and then retransmit them back, if you will, and re-aggregate them, then you would get some sense not only of the local cost of adaptation to climate change, but you could add it up and get the global cost, and then that would be a more trustworthy number than guesses, than derivative economic models that follow solely from the climate models. And so you can, but this is, the vision at the end here is well off into the future. But it's something that I think we will, not in my lifetime, get to. We'll have to.
If you were to couple climate and economic models, I have more faith in the climate models.
Yes, I think Partha, you might have a comment on that.
You're doing fine.
Yeah.
Okay, I think we have time for one or possibly two more questions. There's a person at the end of... You have a question?
And the Grant Kopek down here has a question too.
You spoke about the inertia of the system, and sort of even if we do things now, it was still skewed. Is there any kind of variable in the basket that you can have that doesn't have that inertia, that could potentially be a beacon of hope or like a sign of...
Yes, indeed. And we wrote an article that pointed out that of all the greenhouse gases in the atmosphere, 40% were not CO2. They were black carbon, methane, nitrous oxide, and each of these has a much shorter lifetime in the atmosphere. So you could offset the present rate of climate warming by reducing these gases, and you would get a response in about 10 years' time. So we recommended to the politicians that they do this, and the UN Environmental Program has taken this up and called this a Climate and Clear Air Coalition. We think it's doable because many of the things that pollution control agencies do will also benefit and have these climate benefits. So that all that matters is that you increase their remit to include the short-lived climate forcing agency. Once you've done this, you can only do it once, and then you're back to carbon, and that is the big, big existential problem. But yes, you can offset it. You can buy a little time. You might push off the time that the sea level inundates Venice by 20 years. And if you did that, maybe people would have a little more time to prepare. So it's a valuable one-term thing. It was presented by President Obama to the G8, and they have adopted it as a policy. But there's no action. It's an information sharing international program.
Maybe just related to this, but just to perhaps finish on a note of not complete pessimism. I'm quite optimistic, actually, and I'm optimistic not because I suddenly believe that the world has become altruistic, but because the disbenefits of climate change are so large that politicians are going to have to respond to those. If you look at the cost, PM2.5, the 2.5 micron emissions that you get from diesel fuel, which is, we just heard yesterday, killed 75,000 people in Britain, I think, last year. In Beijing, the cost, or in China in general, the cost of remediation of that particular problem in society is 11% of the GNP of China. 11% of the Chinese GNP goes in the health disbenefits as a consequence of excess PM2.5 emissions. China can no longer afford to do that. You can't afford to spend 11% of your GNP on just dealing with one particular health issue. And that's why China is suddenly interested in reducing climate change. Because when you start reducing PM2.5, lo and behold, lots of other things are also a co-benefit as you reduce CO2, you reduce lots of other things as well. So I believe that there are strong reasons why countries will coincidentally improve their climate behavior because they're busy solving other problems.
In fact, the Chinese commitment, I believe, is based on their plan to reduce air pollution by 2030.
Exactly. And just fortunately, that means they reduce the CO2 output as well.
That will help, yes. So I have a reason for optimism as well, and it really is based on the Paris climate negotiations themselves, not what was decided. But the idea that there's a global consonance of view finally has emerged. And this is an idea that David King has expressed a number of times. And that is that when that happens, a lot of entities in society, financial, business, and so forth, see which way the wind is going. They know the direction a little bit better than they did. And this is going to be a great liberator of innovation. And so he expects to see an innovation explosion around energy and water management and so forth, just because now more and more entities in society that have to align their activities in order to make progress will do so. And by the way, he thinks that the UK and California will benefit tremendously because we are advanced in all of these, not only the engineering technologies, but the social technologies, and that these can be transmitted around the world.
Okay. We started a couple of minutes late, so I'm going to allow one more question. You, sir, at the back.
Grant, yeah.
Thanks. I'm interested in the science push for a basket of indicators versus the policy pull.
That's his job. Yeah.
Well, earlier you mentioned, for example, that they were tuning climate models based on global average temperatures because that's what you cared about. And I just wondered if you've seen momentum for using a basket of indicators from the science community or more from the policy community. When would you think that such a basket might be included in, say, an IPCC?
Well, they're there. The measures are there. They're published. There's not much description of them. In fact, even the ocean heat content, which I think is the most important diagram in the entire IPCC, 15,000 pages, is not in the summary. It's not in the policymaker summary. It's not even in the technical summary. You have to read the whole 1,300 Working Group 1 report before you find it. So they have a lot of jewels in there, which they didn't realize, I think, when they introduced them.
The job is not to produce these indicators The vital signs is not to produce them. I think we know how to do them. But the point is to promote them from data into vital signs that the public and the decision makers will pay attention to and understand in forms that they can understand. So that's the job. We can do it. The intermediate direct risk indicators, that's an area of research, and I think that governments and policy groups will be working on systemic risk, and the techniques that they will use will be related.
Okay, we're out of time, but I'd like to invite everyone to join us just outside the doors here, where I hope there'll be a drink available. But before that, will you please join me in thanking Charlie and Stephen for